Hi there, this is the Chapter 12B test review, and as always, I am the amazing Mr. Jansen. So away we go. If we look at these first couple, we're just filling in the blank with the appropriate definition, reviewing some of our math terms here. The first one, it says a blank is the selection of objects taken in no particular order, and the key here is that it's no particular order, so when order does not matter, that's when we use what's called a combination. Okay. For the next one, it says a blank is an arrangement of objects in a particular order. And when order does matter, when we are looking at things in a particular order, and a key word is arrangements, and it is in a particular order, when order does matter, we use what's called a permutation. Okay. For the next one, it says data that is measured numerically is known as blank. And when we're able to physically compare numbers, all right, and quantify things, in other words, we're looking at quantities is the other key word here. That's what we call quantitative data. So quantitative. All right. In other words, we can count it up. We can measure it numerically. When data can't be measured numerically, data measured not measured numerically, when we're looking at the quality of it, what do you think is best? What do you like the most? We're looking at the quality of things. That's known as qualitative. Okay, so quantity versus quality. Okay. Next one says blank events are events that do not affect one another. Okay, when events do not affect one another, they occur independently of one another. One does not affect the outcome of the other. So these are independent events. The next one is the reverse of that, events that do affect one another. These are dependent events because the outcome of one depends on the outcome of the other. Dependent events. For number 7, it says blank compares the number of outcomes in an event to the total number of outcomes, while something else compares the number of favorable outcomes to the number of unfavorable outcomes. And remember, the thing that compares the number of outcomes in the event to the total, when we're comparing to the total here, and these are some of the key words, we're comparing to the total, we're talking about probability. When we're not comparing to the total, when we're looking at favorable versus unfavorable, that's when we're looking at what we call odds. Okay, and that's the difference between odds and probability. Probability compares it to the total. Odds compares favorable to unfavorable. Number 8, it says blank events cannot occur simultaneously, while this other type of event can occur simultaneously. And this is what we were looking at when we were looking at compound events, when we were looking at our OR probabilities. Remember, the options we had were mutually exclusive, and mutually exclusive events cannot occur simultaneously. In other words, if I'm rolling a number cube, I can't roll a 5 and a 3 at the same time. There's no spot on the die that indicates a 5 and a 3 at the same time simultaneously, so they're mutually exclusive. It can be one or the other, but not both. The other way that this can happen is what we call overlapping, or I like the word inclusive. And I'll accept either one of those for this answer. But overlapping or inclusive events do occur simultaneously. So if I said the probability of rolling a multiple of 2 or a multiple of 3, there's overlap there because it could be a multiple of 2 and a multiple of 3 at the same time if I rolled a 6. Okay, so look for overlapping versus mutually exclusive events. For these next couple, it just asks us to simplify these problems, and we just have to be familiar with what each of these things mean. The first thing, it says 5 factorial. Remember that exclamation point means 5 factorial, which means I do 5 times 4 times 3 times 2 times 1. And I just have to multiply all these together, and that gives me 120. And that's it. For the next one, when I'm reducing factorials, remember I can cancel these out. It's kind of like fighting a giant spider where we want to chop the legs off. So with this one, the 18 factorial and the 15 factorial, they're going to cancel out. And again, I chop the legs off, which means I'm only left with the top numbers, the 18, the 17, and the 16. Everything else got canceled out from 15 on down. Okay, so I chopped the legs off. And then underneath here, the 3 factorial still leaves me with a 3 times 2 times 1. And I can always reduce this further. A 3 times 2 is a 6, so I can reduce the 6 in each of these, which would give me a 3 over 1. And now I can just multiply these. And when I do that, it gives me an 816. And again, the other option here, I don't have to do that extra reducing that I did. You can multiply the 18, the 17, and the 16, and then divide it by the 3 times 2 times 1, which is 6. All right. The last factorial we have here is kind of one of our special cases. Remember, 0 factorial, it's like I have 0 objects being arranged. There's still one way I can do that, the arrangement of nothing. So remember, 0 factorial is 1. Okay? For this next one, this is the combination of 7 choose 3. Remember, our formula for combination is n factorial over n minus r factorial. R factorial. And remember, it's written in this form. It's NCR. So my n is the 7, my r is the 3. So I'm just going to plug these in. So I've got a 7 factorial over 7 minus 3 factorial, 3 factorial. And I would just have to simplify this. 7 factorial over, I start inside parentheses, that's going to be a 4 factorial, 3 factorial. And now from here, again, it's like fighting a giant spider. I'm going to chop the legs off. So when I reduce the 7 factorial and the 4 factorial, everything from 4 on down cancels. I'm left with the 7, the 6, and the 5 over the 3 factorial, which is 3 times 2 times 1. And again, we can do more reducing here, or we can just multiply this out, and it's going to give me a 35. Okay? For the next one, I've got a permutation, and a permutation is very similar. It's going to be n factorial over n minus r factorial. So instead of having that extra r factorial, we're without it. And again, it's still a similar notation, n permutation r. So n is the 8, r is the 3. So I have 8 factorial over 8 minus 3 factorial. And I start inside the parentheses, I subtract. That's going to give me a 5 factorial. And now I cancel these out. Just like fighting a giant spider, I chop the legs off. So I'm going to be left with the 8, the 7, and the 6. Okay? Everything from 5 on down canceled out. So now I multiply these, and it gives me a 336. And that's it. For these next couple, we're finding the number of possibilities for each. And for these, really, the first thing we always want to decide is whether or not order matters. So for like number 14, it says how many ways can the starting lineup of 7 athletes be announced? And since we're trying to figure out how many ways they can be announced, in other words, what order their names can be called in, order does matter here. So we're going to be using a permutation. And again, some of the key words for knowing that order matters is the words like arranged, or if we're lining things up, or if we're placing things in a row. All right, anytime we're doing that, order matters. All right, if we're competing in an event and we're looking at who's getting first, second, and third place, order matters. Okay, so here order matters, so I'm using a permutation. So it's the permutation of, there's 7 athletes, and we're going to announce all of them, so it's the permutation of 7 choose 7. So it's 7 factorial over 7 minus 7 factorial, which is 7 factorial over 0 factorial. Remember, 0 factorial is 1, so all I have here is 7 factorial. And remember, 7 factorial, we're just doing the 7 times 6 times 5 times 4 times 3 times 2 times 1. And that's going to give me a 5,040. And that's it. Okay, so there's 5,040 ways that we can announce the starting 7. For the next one, it says a group of 5 students is chosen from a class of 20 students to participate in a committee. How many ways can the committee be chosen? So I have to decide, does order matter? If I'm placing students on a committee, does it matter what order they're chosen in? No. For this one, anytime we're choosing a team or a committee or a group in which they're not being assigned roles, order doesn't matter. Okay, it doesn't matter what order they're selected in, it's still the same 5 students. It's the same committee. So in this one, we're going to use a combination. Because order does not matter, so it's the combination of, there's 20 students total, and we're choosing 5 of them. And again, the larger number should always be first. It's always the total number of students and then how many we're picking. Right, total number of objects, how many we're choosing. So it's going to be 20 factorial over 20 minus 5 factorial, 5 factorial. And now I'm going to simplify this, 20 factorial over 15 factorial, 5 factorial. And now just like fighting a giant spider, I'm going to cancel these out, chop the legs off. So it's going to leave me with a 20 times 19 times 18 times 17 times 16. Everything from 15 on down canceled out. I still have the 5 times 4 times 3 times 2 times 1 left down here. And again, I could simplify this further if I wanted to. I'm just going to go ahead and multiply these. So when I do this, it gives me a 15,504. The next one, it says a restaurant offers 6 different entree items, 8 side dishes, and 4 dessert options. If customers are allowed 1 entree, 1 side, and 1 dessert, how many different meal options are available? And for this one, since we're only choosing 1 of each, this is just a case of our fundamental counting principle. I mean, I could take this off to the side, and I could do a tree diagram for this and write out my 6 different entree options. And then from there, branch off to the 8 different side dishes for each one. And then from each of those, branch off even more. And then we get all this craziness, and it's insane, and we don't want to do that. So the shorter way to do this is just use our fundamental counting principle. There's 6 ways that I can choose the entree item. There's 8 ways I can choose the side dishes. And there's 4 ways that I can choose the desserts. And so instead of having these giant tree diagrams where we have all these little pieces off of our entree, let me draw this a little more officially. That would be my 1 entree, and then my 8 dishes, and then my 4 different dessert items off of each one. And I'd have to do this for every single one of the entrees. Okay, and this becomes really tedious. Okay, and it would be crazy to do it that way. So we simplify, but say there's 6 ways that this can happen, 8 ways that this can happen, 4 ways that this can happen. Fundamental counting principle says I multiply those options. So 6 times the 8 times the 4 is going to give me 192. Okay, and essentially with a tree diagram, I'd have to count all those up. With this one, I just multiply the number of possibilities for each. So how many ways can the first thing happen, times how many ways can the second thing happen, times how many ways can the third thing happen. That's our fundamental counting principle. Okay, and you get a 192. For these, it says to find each probability. The first one, it says you roll a standard number cube. So I'm rolling a standard number cube, and I want the probability. It says find the probability that a number is less than 4. Well, on a standard number cube, I have 6 numbers. If I want a number less than 4, that would be the numbers 1, 2, or 3. So there's 3 options here. So 3 options that are less than 4. Out of a total of 6 options, so it's 3 out of 6, which of course reduces to 1/2. When you're doing these probabilities, make sure that you reduce your fractions. Okay?